In this lesson, we're going to look at how to determine when functions are increasing or decreasing. We need to be able to find the range of values for x for which a function is increasing or decreasing, and prove that a function is increasing or decreasing for all values of x. So first of all, let's have a look at what we mean by a function that's increasing or decreasing. So function a is decreasing because as we increase our x values or move to the right, we can see the y values going down. The curve is going down. And for function b, as we increase our x values, the y values increase, or the curve is going up. So b is an increasing function and a is a decreasing function. Looking at intervals on this curve, let's decide if the function is increasing or decreasing in those intervals. So if we look in the interval a to b, we can see the curve is going upwards. So in that interval, the function is increasing. If we found the gradient at any point on that curve between a and b, we would find that it was positive. Okay, we can see it's a positive gradient. The tangent at any point would be sloping to give us a positive gradient. So when the function's increasing, dy by dx is greater than 0. Between x equals b and x equals c, we can see the curve is going downwards. So in that interval, the function is decreasing. And again, if we found the gradient at any point between b and c, and we can see if we drew a tangent at any point between b and c, the gradient would be negative. So when the function's decreasing, dy by dx is less than 0. Between c and d, the curve's going upwards again. So in this interval, the function is increasing. So for this interval, the gradient will be positive, dy by dx greater than 0. Let's have a look at what's happening at x equals b and x equals c. So we can see that these points here are where the curve turns. So these are called turning points on the curve, and we can see it's where they change from being an increasing to a decreasing function. If we drew tangents at these points, we can see that they are horizontal lines. So the function is not increasing or decreasing at these points. The function is actually momentarily stationary. So x equals b and x equals c are actually called stationary points. And at these points, dy by dx is equal to 0. So to summarise then, if a function is increasing, dy by dx is greater than 0. If a function is decreasing, dy by dx is less than 0. And if a function has a stationary point, dy by dx is equal to 0. Let's have a look at an example. So here we're asked to find the range of values for x for which this cubic function is decreasing. So we know a function is decreasing when dy by dx is less than 0. So first of all, we're going to differentiate to find dy by dx. I'm actually going to use function notation for dy by dx, which is f dash x, because that's what we're given in the question. And we get 3x squared minus 12x. So let's put that less than 0 to find when the function is decreasing. So now I've ended up with a quadratic inequality to solve. So factorising gives me the critical values of x equals 0 and x equals 4. So don't forget, when we've got a quadratic inequality to solve, we need to draw a sketch. So drawing a quick sketch of this quadratic, 0 and 4, and I want when the quadratic is less than 0, so that's the part of the graph that I'm interested in. So I know my solution to my quadratic inequality is x is between 0 and 4, so that tells me the range of values when x cubed minus 6x squared plus 2x is decreasing. Okay, let's have a look at another example. This time we want to show that x cubed plus 24x plus 3 is an increasing function for all values of x. So in order to do this, we're going to find the gradient function, and what we want to do is to show that the gradient function is always greater than 0, always positive. So let's differentiate first to find the gradient function, giving us 3x squared plus 24. So we can see that this function is always going to be positive because x squared is always positive for all values of x, because if we square a negative we get a positive. If we multiply a positive by 3 and add 24, we're going to end up with a positive. So the sort of thing we could write there to show that the gradient function is always positive is x squared is greater than or equal to 0 for all values of x. So 3x squared plus 24 is greater than 0 for all values of x. Therefore, the gradient is always positive, so f of x is an increasing function. Let's have a look at this graphically so we can see that the gradient is positive for all values of x. So my red curve here is my original cubic function. We can see that that's an increasing function for all values of x because we can see that it's going upwards. But if we plot the gradient function, so there's my gradient function, which is my quadratic, 3x squared plus 24, I can clearly see that that quadratic is always positive because it's always above the x-axis. So if we have a look at this example again, we're asked to show that it's an increasing function for all values of x. So again, we're going to differentiate to find the gradient function, but we need to use a slightly different way to show that this gradient function is always positive. It's not so clear-cut and obvious as the previous example, so the other way we can show the gradient function is always positive is by completing the square. So let's have a look at this. So differentiating, first of all, gives me, in fact, let's use dy by dx this time because we've got y in our notation for the equation of our curve. So dy by dx is equal to, you can have a go at this, 3x squared minus 6x plus 10. So that's our step 1. So to show that 3x squared minus 6x plus 10 is always positive, we can complete the square on it. So this is good revision on completing the square when a is greater than 1. So remember, when a is greater than 1, the first thing we're going to do is factorise the 3 out of the first two terms. So I'm leaving the plus 10 alone and just factorising the 3x squared minus 6x. Now I'm going to complete the square on just the x squared minus 2x. So I'm going to do that inside big square brackets. So halve it, so I'm going to halve the minus 2 to give me minus 1, square it, and then we're going to subtract it. So halve it, square this minus 1 gives me plus 1, then subtract it, and then I mustn't forget to put my plus 10 on the end. So just using some red here, what's inside these curved brackets here is equal to what's inside these big square brackets. It's just completing the square on x squared minus 2x. So let's tidy this up a bit. So I'm going to expand the square brackets. And then finally just simplify the minus 3 plus 10 to give me plus 7. So now we've got the gradient function, the quadratic expression for the gradient function in the completed the square form. We can see that it's always positive. And we know that because anything squared is always positive. So the x minus 1 all squared is always positive. This will always be positive because it's a squared term. So if we multiply that 3 and we add something to it, it's still always going to be positive. So the completed the square form is a really good way to see if a function is always positive. So we would write something like 3 brackets x minus 1 squared is greater than or equal to 0 for all values of x. So adding 7 means 3x minus 1 squared plus 7 is greater than or equal to 0 for all values of x. The gradient is always positive, so f of x is an increasing function. Again, let's have a look at the original function and the gradient function graphically. So here's my original cubic function in red. I can clearly see on this graph that it's always positive. If we then plot the gradient function, which is my kind of dashed yellowy coloured line, I can see it's always positive because it's always above the x-axis. So now I'd like you to have a go at some of the questions from exercise 8D that are listed here. Remember, when you're solving quadratic inequalities, you always need to draw a sketch.